Hello everyone, and welcome to my presentation at the InterPore 2021. My name is Yousef Heider. I'm a research associate at the RWTH Aachen University in Germany, and I will give a presentation with the title Advancements in Suction-Induced Fracture in Multiphase Porous Media, and the focus will be on data-driven multiscale modeling. So as an overview, I will start by short motivation and explain the aim and the methods of which we are applying here. Then I will introduce mainly two machine learning based models for multi-phase flow in porous media. I will talk later on automated procedure for neural network setting selection, and how we implement the machine learning model in the finite element environment, and then I will shortly explain some future aspects. So suction-induced fractures, it's a very important problem in different fields of engineering, especially, for instance, in geotechnical engineering and in soil science. Take, for instance, this example from soil science, the drying-induced fractures, where the water evaporation, it leads to increase of suction, and at the end you will see this this network of cracks which will change the thermo-hydromechanical properties of soil. Such suction has its macroscopic origin, and this would be clear if we look at unsaturated porous material at microscopic scale. We see here, because it's unsaturated, you will see here some air phase, water phase, and the solid phase. And if we look, for instance, between two grains, you will see some water bridges if this material is binular regime. And then you see this curvature. So this is due to the interface tension between the gas and the air phase and the water or liquid phase. And if you want to describe the balance of this material at the lower scale, you may go for the Young-Laplace equation, which describes this very well. However, we are mostly interested in the higher scale simulation. So if we go for macroscopic modeling, you'll find in the literature a lot of phenomenological models, or we could also use data-driven models directly using the machine learning integration in this case. With this, we can find a correlation or a relationship between the suction, so the gas pressure minus the liquid pressure, and the degree of saturation. For the phenomenological model, take, for instance, the Frank-Knuchten model. So it is simply a curve which can be expressed in such an equation, and it approximates actually the wetting and drying paths in one curve. So it's to some extent it's a very rough approximation of the reality. Alternative to this, we can go for machine learning based model using, for instance, this approach which I'm applying in this work. We start by generating a database which will be needed for the machine learning model, and this database will be generated from lower scale simulation, so macroscopic scale simulation, like using the discrete element method or the Latz-Boltzmann method. And we generate the database, and then we use this database to train our machine learning model. So for the retention curve, for instance, we use the recurrent neural network. And once this model is trained, it can then be integrated in the finite element environment as an alternative to the conventional or phenomenological material model. I will go to more details with regard to these issues later. So the aim of this research work is first to apply an accurate and computationally efficient multi-scale approach for material modeling, of course, for unsaturated porous media. And this represents an offline approach because the lower scale simulation is carried out first, and then we take this information separately to the higher scale. So they are carried out in separate steps. And the methods which we are applying, it can be summarized in three major steps. First, we need to generate a database from lower scale simulations. And then we use this database for the training of our machine learning model. It is a supervised learning, and we are applying deep reinforcement learning to automatically discover the optimal neural networks. And as a part of this, we are also generating a trained model. Once we have a trained model, then we can integrate this into the higher scaled continuum finite element environment. So after this short motivation, I will present shortly some machine learning based models. As I said, the first step would be to generate a database from lower scale simulation. And with regard to Porous media, we have some constitutive models which are related to the deformations and others are related to the flow. Namely, we have major three constitutive models, which are first the relationship between the strain and the stress. For this, we apply, for instance, the discrete element methods, where we can model our porous material as a granular material. With discrete element method, we can apply deformations, and we could also apply the Hill-Mandel homogenization approach to figure out the macroscopic strain and stress component or the tensors. We can also apply pore network model to simulate the multiphase flow in porous material, also a deformed configuration. And we could get here a database which includes the suction. We can include also lower scale information like porosity, and then we get as a result the degree of saturation. And then we need some database which is related to the permeability. Simply we apply the Lutz-Boltzmann methods, which solve the Navier-Stokes equation at the micro and mesoscale. We have already the deformed configuration from the discrete element method, so now we apply the Lutz-Boltzmann methods to get a database which includes the pressure gradients and the fluid velocities. So now we have the database, and then we can train our model. For the retention curve, we use the suction from the current time step and also from previous time steps. So this is the recurrent neural network. And the reason for using the values from previous time step, simply because we would like to know if we are on drying or wetting passes. And we could also include the porosity in this procedure. With the machine learning, we can predict the degree of saturation at the current time step. This is roughly how the structure of the neural network look like. So we have an input layer and output layer, which includes our desired output and some hidden layers. And this is an example how the retention curve look like for different degrees of compression. So we have here the compression is or the compaction is reflected through the porosity. And the other constitutive model is related to the permeability. And here we use as input the pressure gradient, maybe the fabric tensor, and the porosity, and then as an output, we get or we predict the velocity in different directions. And then through using some kind of inverse problem, we can predict the different component of our permeability tensor. This is a general approach because if you now have anisotropic permeability, you could also follow this approach. And this is very important for us, especially when we go for the simulation of the flow in the fractures where we have very clear anisotropy. I mean, these material models, which are based on machine learning, can be implemented in the finite element code, but there are some steps which we have to carry out, namely the selection of the settings or the metaparameters of our neural network. And this is what we try to do using automated approaches. Simply, we call this a self-played game of neural network metaparameter selection. And the game definition is we have to apply we carry out sequences of decision to maximize the score. So we make selections so that the trained model with this selection should be as accurate as possible. So the score in our case is connected to the accuracy of the prediction. And the game board this is comparable with the chess. So the game board in chess would be like this 8 by 8 places. And here we have the board would be all possible settings. So in this small graph, we would have 2,592 possible combinations. and the board would be all settings, but first without any edges, so without selection. And the rules here in chess, every piece it has some. You can move it in certain way, in certain rules. And here the rule is that we have to select one of these options from each subset. So we have to select only one neuron type. We can select only a specific number of hidden layers and so on. And the action is one selection. The state is the state of this game after carrying out this selection. Reward, you have the final reward, which is in chess would be win or lose. And here we have the final reward is the accuracy of the prediction. And there are like intermediate rewards. And this evaluation is carried out at the end of the, in chess at the end of the game, and here at the end of each selection. This is carried out in using the deep reinforcement learning, which is based on the reward hypothesis. So in this case, we proceed from artificial intelligent agent, as you see here, which represents a Markov decision process, which uses exploration and exploitation, so exactly like in robotic, to discover the best actions. So it means a best selection that maximizes the reward via interaction with the environment. And the environment would include the data sets, the validation procedures, and so on. From this selection, the agent receives new states and rewards. And this is, of course, an iterative process. So in this, at each iteration, you have to carry out several selections and compare this to each other. And of course, this artificial intelligent agent represents a mapping from state and reward, as you see here, state reward, to probabilities of selecting each action. This selection is associated with value function, which allows to predict the future rewards. And then also this Markov decision processor is augmented by the Monte Carlo tree search, which is a very modern search approach. It's also applied in games. And first, or at the end, when we make the selection, we have to compute the score, which is scored to be, which is scaled to be in the range between -1 for a very bad score and 1 for a very high score. So, for example, for the optimal selection of neural network settings, we can compute the score in this relation. So we compute the score based on the accuracy with respect to the prediction of the which is related to the training, the validation, and the testing data sets. And we consider search space, which includes all these options. So we have several neural types, hidden layers, and so on. So in total, we would have from this sets of settings, we would have 48,000 admissible combination. But we don't want to try all of them. We want to try only small number of them, like 0.9% of them. Which corresponds to 420 possible combination. We see that our algorithm, it reached to a very good accuracy after a very short time. So after 2 or 3 deep reinforcement learning iteration, our score it's almost 1. Of course, each iteration includes also episodes, so 20 episodes, which will be compared to each other. And you will see here a schematic illustration of the decision tree, how the selection looks like when we apply this deep reinforcement learning algorithm. For more illustration, I will show here how the resulting model from the which is based on the selected settings perform. So we have in this figure here, we have the score is -1, which is very very low. The red line is our belongs to our testing database, so it's the exact, let's say, solution. And our blue line would be then the curve which results from the from the trained model, which corresponds to the score -1, which shows a very bad prediction. Then by repeating this iteration, so the deep reinforcement learning iterations, the scores improve. So our score now is 0.3, and now we see our machine learning model is performing much better. We still have some problems here and above. And then by continuing the iteration, we get a very high score, which is 0.908. And then our trained model is showing a very good performance. Now we can go with this trained model to the finite element application. So take this boundary value problem. It's we have a two-dimensional domain, unsaturated, with water and air phases. And we apply here at the left-hand side, we apply negative pressure, which is followed by positive, so section, and then we have injection. And we are looking in the domain at two issues. First, we would like to compare the accuracy of the results of machine learning. We compare this with the performance of the phenomenological retention curve of Frank Notion. Which one is more accurate? And also, we are interested in the stability of our machine learning model to have any stability problem. This is what we will see. So first, for the accuracy, it's very clear our machine learning model can predict both the drying and wetting passes, whereas the Frank Notion model is only one curve. So the accuracy is by far for the machine learning model is much better. For the stability, we would have some problems in the machine learning model because it gives you discrete values of the degree of suction of the degree of saturation, and because we are just replacing the constitutive model in our balance equation, we would have this term, which is a derivation of the degree of saturation with respect to the suction. We need to compute this from the machine learning prediction using methods like the finite different methods. That's why we would have some kind of explicit step, and this leads to some restriction on the stability. So we need to find like a critical time step with which we have like a stable solution. We would not have the case this stability problem if we have like Frank Notion model, because this is a continuum function and we can apply the derivation much easier. We see the difference in accuracy when we look at the flow direction. For instance, after 10 seconds, we see the flow direction with both Frank Notion and machine learning model exactly the same. However, at some point we see that the Frank Notion model will predict flow direction, which is exactly the opposite of machine learning model, and this is a like serious issue for some problems. So the prediction here is clear for the machine learning model is much better. For the future work, we are working on extending our machine learning approach in order to overcome like stability challenges that I mentioned in the context of finite element implementation. We are extending this approach also to capture the flow in fracture. And we are also extending this approach to predict material parameters in connection with experimental data. And this can also be applied for the design of engineering systems and also other problems. I would like at this point also to acknowledge the support of Professor Vashim San and the team at Columbia University, and also Professor Bernd Markert at the RWTH Aachen University, and all the support of my team at the RWTH Aachen and I would like also to thank you for your attention, and I hope we will meet then live during the conference. Thank you so much.